this is where we were. And basically, this led us to the question that Ozai said, well, why don't you call the circulation of money not just the money, or money supply, whatever it is. And here I show you that because of the way we define money, this is actually. And the theorem that symplectic geometers would use to identify that this is the case is what's called Stokes theorem. So celebrated theorem.
Er staat wel op de verkeerde microfoon.
Oh, ik denk dat je jouw microfoon. Okay, so this helps. I put on my microphone. So let me start again. This is where we left off. We've achieved quite a bit. So purportedly, we know now what money is. It's just a little bit of density. It's distributed all over phase space, okay? So the more goods you have, or the higher the prices, the more money you will need, all right? So money is it's just this thing lying uniformly here over the phase space. So these things, these are called two forms. They're also sometimes called densities, okay?
Sorry if it's going to deviate a little bit from the
No.
Is it that necessarily a circle in the phase plate?
No, that's just for the harmonic oscillator that I integrated like that. You can do anything you like. So yeah, you can also have a ellipse, but you can also have a particle or just an agent in partial equilibrium. So a free particle, right? And then you can say, well, I'm going to calculate, this is what these guys do. So they keep the price level constant, and they say, I'm going to integrate this until, some time or something. This is then a velocity, then a year, and then this will be this area, It's just in general area, and then, it would be, this would be the cycle, I guess. Huh? So this doesn't mean that it necessarily is a circular thing. It just means you integrate it, you come back to where you were, right? Huh? Okay. You could also integrate PDQ, right? That's this thing, huh? And then you just have to go up, huh?
May I ask, in that left picture you drew, what do you take as your reference frames? Like, what's your zero? Because if you put your P at zero, then there's no surface area under the function.
Sure. What you do is, here's what you do. So you have, this is PDQ, right? Yeah. At one level of P, and then I'll do another one, now here, a little bit smaller, P minus delta P, right? And this is P, right? So that's this area minus this area. And the difference is this little block. Right? So the expenditure is an amount of area here, right? And I want to see how that amount of area changes when I change the price, right? Huh? There you go. This is the price change. Huh? Okay.
So it's irrelevant.
Yeah, the shape is irrelevant. These are infinitesimal things, You can put it, and where it is, I could have put it here, I could have put it there. It's just that I draw it as a finite thing, so it looks like I went down, but I could have gone up. I could have drawn it as a little circle, because this thing looks like a rectangle, but it really isn't. Who knows what the shape is? The shape is just irrelevant, So this thing, dPdq, you can draw it as a rectangle in these coordinates. But what if I say this is r, so dr times, so suppose I use different coordinates, right? So I'll use some polar coordinates, then it will look maybe something like this, right? Huh? Huh? So this will be r, this will be dr, huh? This will be d theta, right? Huh? So what will be this area? Well, it will be r times r d theta, right? Huh? Sorry, dr, so that's this thing, times, no, r d theta, because r d theta. right? R d theta is different. This length here is r d theta, right? The
Oh,
angle
right.
is, huh? Okay. So then this same, so dp dq becomes r times dr d theta, right? Huh? Huh?
Yeah, maybe also like a little side note, this whole business with the RDT, that's something we learned in like first year of vector calculus, and the whole business with little d's and the forms and the product and all the operations is just meant to be a generalization for all that stuff that we learned. That was like very ad hoc fashion to sort of talk about it. When you talk about very complicated spaces, then you need like a little more beefed up version of all those rules, and that's exactly what will be at the special product that Max probably goes to in a minute. Try to do, right? So that's basically why it exists. Gives you stuff to integrate over.
Otherwise, I'm talking about the curl and the gradient and the divergence and then blah. And you know, you get all this curl of the grad and of the vector. You don't know, and you just lose track. So my trick here is to use this d like a small change. You know, and be quite liberal about what the exact meaning of this is at this point, and just get you through the thinking, right? And then later on, for as much as we need it, we can fill in the exact definitions, which is what Emil is talking about, okay? So you got the curl operator, and you have the idea of the curl, that if you make a tiny little circle, that you pick up some circulation or not, right? Okay. And then you have the gradient operator, and the idea that is when you make a small motion, you're going to accumulate a little bit, right? And it's the direction of the greatest increase and all that. So there's all these intuitions, and what this is trying to do is have a notation that focuses on the intuitions, and at the same time there's all kinds of definitions. This is called an exterior product, right? Or a wedge product instead of just without it, you know. It's got all kinds of stuff that you just don't want to know just to get going with this, you know? What I want to do is just take an engineering approach to this. Like, we use a lot of math and, you know, like matrices, and why does it work? Well, I mean, maybe you know, maybe you don't know. You just know that it works. You know, you take your A matrix, you throw that in, and you know you're going to get that out, right? So, and it makes sense, and, so that's the approach to math I'm taking here, all right, for the first pass. So it's the opposite of what a normal book on this subject would do, is first explain to you all the math, and then in like 2 minutes tell you what's going on. Here I'm spending all this time telling you what's going on, and then later on we can see what the math exactly is, all right? But I think it's working because I'm getting good questions, right? So your question is more, why is this below and this? And the answer is, look, it doesn't really matter. These are all infinitesimal objects drawn, you know, now to scale. And you see, why do I use this? Why don't I just write dp dq? Well, because this already assumes I have chosen this is the price and this is the quantity. But I could have thought theta is the quantity and then R is the price, you know, or R is the price and this is the, you know, That's what you do when you have a rotational analog, right? You make an angle and then the momentum, you know, for instance. And then it would look like this, right? Which is not the same as this. You know, this is like a little wedgy thing like that, with a little, whatever, it's irrelevant. They're all this abstract thing that just to me looks like this little block in these coordinates, all right? Okay. And that's also the input of this statement. I could have written here dp dq, and then you're integrating all these little blocks, and then here, instead of alpha p dq, and then you're integrating all these rectangle things. But what does it matter? You just take any old coordinate system and this works. And this is the point of this canonical one form. You see, it just says it is what it is, independent of the coordinates. Now, you could call it p dq or r d theta or no, it should be r squared d theta, whatever, right? Half r squared d theta, because the derivative would be r dr d theta, right? Huh? So, you know, it's all irrelevant, okay? This is just about money, and you later, you determine in your research what are the best coordinates, what is the way you want to look at it. But what you got to do is you got to pair the price with the quantities, okay? That's the critical thing. So you keep inventory. And whether you're buying inventory in combination tires with the rim or just tires and the rim separately, right? I don't care, huh? You know? Okay? The problem, and that I think differential geometers have the same problem, is this coordinate system is just so handy. It has a name. They call these PQ things, they call that Darboux coordinates. Whatever, right? Huh? So, and then they start proving this, and then they worry about things, whether they can choose globally this thing, or they got to patch it together with charts and stuff. All right, huh? Because in flat space it works, but if your symplectic manifold is a sphere or something, it won't work, right? Because you can't. Some of these p's they jump to infinity or something. Okay. No, I like these questions. So you're not obstructing the flow of this, because I'm really trying to get the concepts across here. Okay. All the symplectic geometry you can look up yourself. Huh? All right. Now this equation of exchange, I actually, it's interesting to, I read a few, I looked up, I had this in my mind, and then I looked it up, and particularly I looked it up on Wikipedia, not because it's such a brilliant thing, but more to see how people talk about. And what is interesting to see is that basically that's what this is saying, okay? That you can have a relation between the total money supply, this M here, so this is M, huh? And this other integral, okay? But they simplify it. They don't have integration, so they'll be messing around, and you'll see all these comments that this doesn't work because the P can change, you know, the price can change, so therefore the equation is invalid, and then somebody made a modification that basically comes down to doing this, right? And then there's some other things. It's pretty interesting to read and to see how this interpretation would take care of the general things and a lot of the complications they list. Right? I don't want to get into it too much. It's a central thing in economics, because they're always searching around for what money is, and some people feel it's a quantity. That's the way we're looking at here, and other people feel it can be, and this and that, you know. So we'll see in the course of, as we go on with this, that this is the basis, this unit of account. And then from that, we can see how it's a medium of exchange. And probably as an economic engineer, you already see it, because, well, kind of feel where it's coming from. Because if you look at your Hamiltonian total surplus, it consists of the kinetic energy, which is the kinetic surplus. That's the stuff in exchange, right? That's the surplus in exchange. You know, now that's the expenditures you make because you're swapping stuff with somebody. But they're also the potential energy. That's your potential surplus. That's the stuff that you have in storage, you know. So you can see how it could function. If you have kinetic energy, at least there is some, and that's the basis of potential energy anyway. It is also a medium of exchange, because it can be used in that case. It's a little bit further along in our lecture, all right? And then I believe that the last one is the store of value, right? Now, maybe that's potential energy, maybe not. We'll leave this all alone for now. Then again, I wanted to talk a little bit about what two forms are. I'm going to skip that, and I'm going to get on with the business. And then if we have time, we can go and talk a little bit more about these details, all right? So now I have these concepts. I have this concept of money, of expenditure, and all of this. I have basically done nothing. I've only done accounting. Now, an accountant cannot tell you how your business is running. He can only keep track of where the money is going. You still have to tell me how you're going to run your business, okay? So in addition to all this symplectic geometry, to move on, you need something a little bit more. And what you need more in the mechanics case is, and in the symplectic geometry case is a function that's called the Hamiltonian, okay? For economics, it says, all right, accounting is all nice and well, but you'll need to know what your surplus is that you're making and you potentially expand it in order to tell me what it is you're actually doing, okay? And this surplus is specified by this function that's called a Hamiltonian, all right? So on this space, and maybe it's good now to go back to this, this slide here. So here is a general space. No, this is too confusing. I'm gonna do it right here. So this is our phase space, okay? And you know what the Hamiltonian is. It's a function of both price and the stock you have, okay? And it gives you a number, right? Huh? So what does this function do? It takes any point here, say this point, and whoop, maps it into this real line, right? Which is this value h of the Hamiltonian at this point, okay? Nothing special here, right? And what you can do is you can look, what about this point here? Well, it could be that it maps to the same point, right? What about that point? Well, maybe that thing goes, a little bit smaller, right? That will be going over here somewhere, right? Huh? But this is a line and this is a plane, so it's clear that there are different combinations of price and stock that will give you the same value of the surplus. And of course there is, right? There are different combinations of kinetic energy and potential energy that give you the same total energy, right? And you can plot all these combinations and they lie on the circle. And of course they do, that's just a circle of constant energy, right? And all you do is when you vary this point, you look back and you see all these different level lines, all right? So you can think of this function as sort of a mountain on top of here. You're climbing this mountain, right? Huh? Okay? That's the picture. And you want to know how steep the mountain is, so what you do is you take a point right next to it and you'll look back what the level line is there, and I straighten them out because I want to look at something linear, and I straightened out both level lines and I flag the uphill direction, and that's what I call this dH. That's the differential of h, that's the gradient. But it's normally what people do is they give the direction of the greatest increase as the gradient, right? And that will be this, all right? Now, you can ask me, why don't you just do that? Why do you invent this other thing, right? Huh? Would you have an idea why I'm not doing this? Huh? It's a subtle issue. Why wouldn't I do that? The problem is that there's no notion of direction here. I could have chosen a completely different dimension here and the thing will be sticking somewhere else, right? I have no notion of angles in this thing, in this space. This accounting doesn't tell me what is a direction. So I can't look at the direction of the greatest increase. But what I can do is just look at these two level lines and see how close they are together. All right? Okay? And that's the idea of a one form. It's like a direction of greatest increase, except without the notion of direction. Huh? Okay? And it's enough. You don't need the idea of a direction. A direction is something else. In complex number, you have a direction. So you have some kind of way of having a compass and a thing, and you usually need a metric. Okay? We don't have this here. We don't want it. We don't want it. Okay? So this is what you do. So this thing here, this is the Hamiltonian is some constant E, okay? And this thing tells you what the gradient is, all right? You know, so you can, when you walk in a mountainous area, you can see all these level lines, and you see a number and there another number, right? And it tells you how much it increased. So the closer the level lines are, the bigger this thing, the gradient, right? Okay? So it works in the other way as a vector, okay? Huh? Now, we know what H is, right? H gives us the total surplus, right? Say per unit of time, all right? Huh? So what can we do? When we want to increase the surplus we have, we would have to grow the surplus. So instead of H, we want to go to H plus DH, right? Okay, then we're making more surplus, all right? So from here, we want to travel maybe to there, right? Okay. So that is like a gradient, and that's why I call this the surplus gradient, okay? It is a one form, and if you expand it, you will see that in order to go up, you'll need to have this amount in the Q direction and this amount in the P direction. All right, that's just a chain rule, okay?
It should be remove the minus sign on the top line of the case of the minus sign once we switch,
This one I want to keep, right?
yeah, so the bottom line.
This one has to be a plus, you're right. Huh? Thank you. Thank you. Now what happens when I just do something? I'm not saying yet that I'm a harmonic oscillator. I'm just going to do something arbitrary, right? Then what will happen is I'll follow this vector, okay? This thing has two components. This component will tell me how much I'm increasing my stock per unit of time, and this component will tell me how much I'm increasing my price per unit of time, all right? Huh? Then what is the actual increase in my surplus, right? Now, what you can do is you can say, and that's why I like these pictures, I want to see how many of these level lines here I'm going to cross. Then I get the rate of increase, okay? So here it's about, what is it, 2.3 or something, right?
How do we define how many of these level lines we define?
Well, you just look at the picture, right? So here is the vector that gives you the velocity, the phase velocity, right? Huh? And here's the picture of these level lines, right? Of course, I have to go on the limit as they get closer, right?
Yeah,
Huh?
but you just drew two arbitrary level lines. Right?
No. Listen, these are not arbitrary. I did, but I have them. I have this function, and I map it in here. And this is this point, say 10, and this one is at point 11, right? Huh? You see? I drew it with an increase of 1.
Yeah, you can only do these components if you like choose this with like.
Yeah, but I define here a step, and I'll do that. And then I can define this one. I also have a step, and then I let the step go to 0. But I do it for both this and this. That's the process of a limit, right? So you can say, here's a path, and I make a step in time, but I don't want to do that. I'll make a step smaller, and I'll divide by the step size. And that's what I do here too, right? So I'll make the step smaller and divide by the step size. Huh? So I get this differential object, right? Huh? So here, I make the step smaller, I divide by the step size. And then here I can multiply again by the step size. Huh? Okay? That's just a usual limiting process. But what you got to see is these things work together, and this working together, that a differential geometer will write it this way. So we said I'm walking at this speed up my mountain, and so much in the x direction, so much in the y direction, and the mountain is going up like this. So that means I'll accumulate so much height per unit of time. Okay? All right? So here, I'm accumulating this surplus per unit of time, or this much energy per unit of time. And what is the change of energy per unit of time? That's exactly the power, right? Huh? And how do you do this calculation? You do that exactly through a sort of inner product kind of thing. So you have this vector x, has components Q dot and P dot. This thing has components that and that, which are equal to minus F and V, and I'll just multiply these together. What is it? Is that right?
Oh, but oh no, that minus 10 can stay.
You can stay, yeah? Just calculating it out.
Yeah.
And that's why you'll find that in certain cases, these are 0, right? Huh? All right?
In autonomous case.
In top. Huh? All right. What happened here? Okay, all I'm doing is a visual inner product kind of thing, row vector by column vector, matrix calculus, blah, blah, blah. All this irrelevant. I just want you to see, how a power calculation will just go here, okay? Huh? So with a power calculation, you need to see that if you change your state, how much the energy changes, but you also need to tell me what you're actually doing. Right? Huh? In economics, I need a function called the surplus function. It tells me how my surplus changes when either the price or my stock changes. But at the same time, I got to tell you what my activity is, what I'm doing. And if I'm doing that, I can tell you the actual rate of increase of the surplus, or the surplus growth. Okay? This is what's happening here. Okay? This is something that you can read off using this geometry. This is something they have special notation for. This is called the interior product. I kind of don't want to burden you with this. I want to have you able to see this simple picture. You need to know how steep the mountain is, and then you need to know how fast you're moving, what direction in that mountain, in order to know how much height you're acquiring per unit of time. So you need these two ingredients. The one is a vector, and the other is a covectoral one. They act together, right? The one tells you how much you're going to increase, and the other tells you, the vector tells you what you're actually doing in order to get this growth, okay? That's the picture here. Now, as you can see, there's one direction that is kind of automatic and for free. That is namely when I'm not growing my surplus, right? What's the only way that I can go if I not want to grow my surplus? Well, I can't make any headway in this height, so I have to go along a level line. I have no choice then, okay? So if the surplus is constant, or if energy is constant, I have to cycle along here. Now, then I come over here, then there'll be another potential increase in the energy. So I gotta keep level with that. I have to keep walking on a level line, right? Huh? Okay. You see that? So that level line is what I will call the business cycle, okay? So if you're just going through your business cycle and you're not growing, what will happen if you are the harmonic oscillator? If you're just a dealer, you'll just be cycling along on this circle or ellipse or whatever the heck it is, right? If you have another Hamiltonian, another surplus function, excuse me, maybe it looks like this, then you'll just be cycling along here, right? Or in that direction, I don't know, huh? You got to figure it out. This thing, this flow is what is differential geometrists call the Hamiltonian flow, all right? That's the flow that indicates the business cycle. That's where the power is 0, huh? Okay? Then you have another one you can do, that's your growth. So you can go like, oh, find this direction of greatest increase, So you'll have no component going along here, all right? And that will be a pure growth kind of thing, all right? Now, in order to accumulate money, you've got to do both. So if you're just going the business cycle, the amount of your money in circulation, that's not going to change, right? You just keep that. If you grow, then that amount will change, all right? If you're just growing, but you're not doing anything otherwise, you just have all this potential income, you're going to sell all these beautiful golden toothbrushes, but you're not going through your business cycle. So you also don't make money. So this money is a two-dimensional, Okay? Let's go to the next slide. And this business brings us to the end of our story, namely the big enchilada results of differential geometry, how we get Hamilton's equations and equations of motion just from this definition of money and then this specification of a surplus function. Okay? Now, how does that go? All right. So here I'm at this point. And remember what money is? It's like this little piece of area, right? So it doesn't matter what the orientation is. I draw a little square. That was the thing we had before, which is the change in the expenditures. Okay, this is the unit of account. It's sitting right there. Okay. Now, one way to see that is that if this is the change in the growth, then there is another change here, right? Which is the accumulation of how much of the business cycle you went through, right? That's your phase change. This is why it's called the phase plane, right? So this the phase of the business cycle is this, okay? Now suppose I cancel that out. I just go along the business cycle. That's the Hamiltonian flow. Then all that's left for me is to grow, right? That's what this equation is saying. If I go along the Hamiltonian flow, so if I just go along the business cycle and I'm trying to make money, then I still have to do a growth. This is the amount of growth that I still have to do in order to get my increase in money. All right? That's what this is saying. This is the big result. You can write it out in coordinates. You'll see this is some kind of vector. This is also a vector. This guy here becomes a matrix, and then you can figure it out here in matrix multiplication. This is sometimes called the J matrix, and they have all kinds of names for it. Why? Because J squared is minus the I. Now, this is kind of confusing. Well, let's not confuse you further with this. This is just the engineering matrix equivalent, what they would use in Port's Hamiltonian systems. They will write it like this. But this is the picture, right? This is the picture, right? It tells you what's involved when you have a system. You have two motions. You have the business cycle, where you're not growing, and then you have growth where you're not cycling. You put those together, you'll get money, all right? And a small increase in money, dp dq, that's omega, huh? All right? Okay. And with that, you get Hamilton's equations, because if you solve this guy, if you just write this out, all this is saying is, damn.
Yeah. Now I think I am.
This should have been a P here, and this should have been a Q. Is that right? Huh?
Yeah, you can switch it up. But you did it also on the other one. Yeah.
Yeah, I messed it up, right? Huh?
But you messed it up differently twice.
This one I messed it up differently. This was done 5 minutes before I did it, and I kept messing up, and I said, okay, whatever. Huh? But the point is that here, if you do this multiplication, this says Q dot is what? dH/dP, right? That's correct. This is Hotelling's lemma. So this part is Hotelling's lemma. Huh? And this one says minus P dot equals dH dQ. And this is just the scarcity law, right? And it's right. To me, I always mess this up, right? So thank you. Huh? And these are together, they're known as Hamilton's equation. They're the same as this. Here I inverted it. Whatever. Huh? I told you this lecture was going to focus on ideas, so obviously you can see I lost myself in the ideas and the pictures so much that my disinterest in the actual calculation leads me to make one mistake after another on these matrix things. I actually don't like these matrix calculations. Just, you never know what, you see, well, what if you see this equation, even if it's right, what does this tell you, right? All it looks like is a neat trick to put two equations into one form, right? That's it. And what's the point? You know, huh? What's going on here? Where's the business cycle? Where's growth? What's the Hamiltonian flow? It doesn't do anything to me, you know? Huh? Then I go to this picture, I see immediately what's going on, right? I have this thing here, that's this matrix, huh? And somehow that thing can eat this and give me, huh? You know, the growth gradient.
But if you want to couple stuff together and you have this picture in your mind, then those matrices are
Really good.
And
If you
then you should be very careful not to screw them up, because then otherwise you
yeah, your whole system doesn't
yeah,
work. Right. So for somebody who is applying this, you better get this right. Okay.
At the end of the day, we're economic engineers.
We're engineers, yeah. So we use matrices because MATLAB understands matrices, and this is the way you got to do it. But the problem with matrices is the interpretation and the thinking gets very removed, you know, and you may have noticed that in your own courses, especially in controls, that you have all this apparatus and you'll learn how to multiply 20 million matrices one another, and at a certain point you just think, well, what the heck did I do? But then you pass your exam, filtering or whatever, you think, well, whatever it is, it was good enough, so let me just move on with my studies, all right? So, yeah, so the problem, if you do this in economic engineering, this is a new field. You got to kind of think through how you're going to apply these matrices to do these calculations. And you can only do that if you see what the different parts are, you know? And for me, I'm going to end here. This geometry there's all these equations, Hamilton's and this and Hamiltonian flow, and it all looks weird. And then you know, then as an instructor, what I want to do is say, well, economically, the Hamiltonian flow is equal to this, and I lose track. I can't just say, well, it's the business cycle, you know? Why? Because I have no idea. I just know it seems to work, right? Huh? So only by going through this and thinking about it this way, does it seem to make sense to me that this symplectic 2 form is money, that the tautological 1 form is indeed an expenditure. It's got to be, right? Huh? That the tangent bundle, the phase plane, is precisely this matching of an inventory ledger with a general ledger, all right? And that the introduction of the surplus is precisely the point where accounting and economics sort of meet. You know, you can do so much with accounting, but you can't specify what you should do, right? You need a CEO, not an accountant, to specify the policy. You know, what are they going to do? How are they going to increase their stocks, and how are they going to decrease their price? You know, this is important, and the only thing that will the only motivation, the only item that you need extra is surplus, which is for a company the profit, and for an individual the utility. So you need this utility, and once you have the utility, you can convert it into the indirect utility or the surplus function, you know, and then you're rolling, you know. We're using this mechanism, you know, and then you have appropriately monetized everything. Okay. So the monetization itself, which is a big step, of course, towards a real economy, that's done by the symplectic geometry and the tautological 1 form. It says PDQ is the thing you got to be looking at, independent of this alpha, independent of what you choose, a P and Q and R, I don't care. But this is the thing. It's got to do this when I write these abstract equations, all right? Huh? And then you say, well, okay, now I need one more thing. I need to know how my profits are coming from, or as a consumer, I need to know where my utility is coming from, you know? Huh? What am I feeling? You know, what am I thinking? What am I, and then I can figure out what I'm going to do, right? So those are the 2 steps. So that's the part of what we would call economics proper, all right? So then you express your behavior in terms of a monetized economy, not just an exchange economy where you're sitting there like Robinson Crusoe exchanging some goods with a monkey or something, but in a monetary economy where the exchange goes through a price change, okay? And then you can, through a transformer or some other device, inductor, mutual inductors, get some other good and influence all of this, all right? Huh? So that's the upshot of this. And so it gives us kind of a whole fresh way of looking at the interplay between accounting and economics, and it gives us a beautiful, in my eyes, picture of how you can see how this is going. Now, the last bit I skipped over a lot, and I'm happy I did so because it would have taken much more than I'd hoped. But maybe someday, when there are questions in a Thursday session, we can go through this for those, or I can talk to those who are really interested in that. All right.
Speaking of which,
All right, coming Thursday.
do we have anybody for coming Thursday?
We don't?
Yep.
So maybe we can sort of stop the recording?
Yeah.
Huh? Do I press this button here?
Yeah.